All right, today we're going to start a new chapter, chapter 4, exponential and logarithmic functions. So these are two new types of functions we have not covered before. We just covered the polynomials in the most part of the semester, and then did a little bit of rational functions, and then we have the exponential and logarithmic functions. And there are also basic functions. But we can start from the inverse functions in 4.1 to begin the discussion. So let's give a brief introduction of inverse functions. So what does it mean by inverse function? If the ordered pairs of function g or the ordered pairs of a function f with the order of the coordinates reversed, then g is the inverse function of f. So that's the definition of inverse function. Basically, if you have a function y equal to f of x, then you define a correspondence between x and y. Namely, you give a value of x, and then you get output of y after the operation of f. But if you consider x as a function y, so then you have the input of y and you get output for x. Then you define a new function in the reversed order, and the new function is called the inverse function. Okay. Um, Now remember, a function has to be one-to-one to have an inverse function. Okay. That means for each value of x, you get only one value for y, but at the same time, for each y, you only have one x corresponding to it. So that's called a one-to-one. Okay. So the notion of inverse function is essentially to consider this correspondence in a different order. It really it is about which is independent variable and which is a dependent variable. Okay. So in the case of y equal to f of x, x is the independent variable that can change freely. Y is the dependent variable that changes because of a change of x. But if you consider it in the other way, then you consider y as a free or independent that can change freely, and x as an output or a function of y, and it changes because of change of y. Then you define another function from y to x. Okay, so x is a inverse function of y, a function of y, and we call that function the inverse function of f. Okay, that's what it means by it. A lot of understand what it means by inverse functions after they take algebra courses, and that's exactly what it means. A one-to-one function can be determined by the horizontal line test. Okay, so we know a function can be justified by vertical line test. If you draw a vertical line, then the graph of the function can only intersect any vertical line by at most one point. Okay. Similarly, if you draw a horizontal line, then a one-to-one function can only intersect any horizontal line by at most one point. Okay, so that's the horizontal line test. Let's talk about one example of one-to-one functions. So the function y f equal to 2x is one-to-one. So you can see the graph is a straight line with slope 2 and passing through the origin. And if you draw any horizontal line, it intersects the line at one point. So that's a one-to-one function. by using the horizontal line test. And you can easily find the inverse function to be y equal to 1/2 x. Okay. I will discuss how to find this inverse function algebraically later. The notation for the inverse function is f inverse f to the -1. It likes f to the -1, but it reads as f inverse of x. So the inverse function of f is f inverse x, which is 1/2 x. Okay, in this case. Now, there's an important property of graphs of a function and its inverse function. Namely, the graph of f inverse is symmetric to the graph of f with respect to the graph of y equal to x. So what it means is if you draw the graph of f and f inverse in the same graph, then you're going to find these two graphs are symmetric with respect to the 45-degree line of y equal to x. So, for example, in the last example, we have function f equal to 2x and the inverse function f inverse equal to 1/2 x. So if you draw them in the same graph, we get y equal to 2x and y equal to 1/2 x as its inverse function, shown in the graph with the red and the purple. And now if you draw the graph y equal to x, that's a 45-degree line in broken line in the graph, and you can see the red line, the purple line are symmetric with respect to the 45-degree line. Okay, and this is true for all functions and the inverse functions. And one of the properties of inverse functions is if you compose a function and its inverse function, you get an identity function. Okay, in either order. So f circle f inverse. So that means f of f inverse of x by definition, and that will be x. So if you consider f of a circle f inverse as one composite function or composite operation, and you give a value of x, and then after this operation, you get back the value of x exactly. Okay, that's called the identity function. And if you reverse the order, you take the composition of f inverse with f, which is defined as f inverse of f, you also get the identity function x. Okay. So, for example, the function f equals 1/3 x plus 2. You can easily show that it's 1-to-1 is straight line with slope 1/3 and the y-intercept 2. And using the horizontal line test, you only get one intersection of the graph with any horizontal line. So that is 1-to-1. And it has a inverse function f inverse equals 3x minus 6 if you do that, as we will discuss in a few minutes. And then we can verify this property of composition f with f inverse. So f composed with f inverse is f of f inverse, but f inverse 3x minus 6. So that's f of 3x minus 6. So that means you can replace x by 3x minus 6 in f. So you get 1/3 times 3x minus 6 plus 2 if you replace x in f by 3x minus 6. And the 1/3 distributed to 3x minus 6, you get x minus 2, and then you add 2. The 2 cancels, you get the x, right? So that verifies the first identity on the top, and you can also verify the second identity. You compose f inverse with f, so that's f inverse of f, but the f is 1/3 x plus 2, So you replace x by 1/3 x plus 2 in f inverse. So that's 3 times 1/3 x plus 2 minus 6 if you change x in the function of f inverse by 1/3 x plus 2. And again, you distribute 3. In the first part, you get the x plus 6, and then you subtract 6, you get the x, the identity function. So we verify this property of inverse function. All right. Okay. So the last topic for this section is how to find the inverse function. You follow 4 steps. Step 1, substitute the y for f. That's just change the notation. Step 2, interchange x and y. You just change x to y and y to x in the equation. Step 3, solve y in terms of x. Okay, you just solve the equation. Step 4, substitute the f inverse for y. So that's again just the notation change. So let's just do one example of finding the inverse function of f equal to 2x plus 1 over x. So here x is not equal to 0 because it's in the denominator, okay? So step 1, substitute y for x or for f. So you just change the fx to y from the previous equation. So we get y equal to 2x plus 1 over x. Step 2, you interchange x and y. So you change y to x and x to y. So we get x to x on the left equal to 2y plus 1 over y on the right. Okay. Step 3, you need to solve y in terms of x. So you need to solve for y. So you can easily do this by first get rid of the denominator by multiplying y on both sides of the equation. So on the left, you get x times y. On the right side, the y cancels if you distribute y on the two sides. So on the right side, you just get 2y plus 1. And then you move 2y to the left, it becomes negative. So x, y minus 2y equal to 1. And then you can factor out y on the left to get x minus 2. So y times x minus 2 equal to 1. You just get 1 left on the right. And then you divide by x minus 2 to solve for y, right? So that's the standard procedure for solving what? Simples. We talked about this before. Simple equation. So if you divide by x minus 2 on both sides, you get y equal to 1 over x minus 2. And then in the last step, step 4, you just change y to f inverse. So then f inverse of x equal to 1 over x minus 2. So that's the inverse function for the original function f. All right. Any questions? So it's pretty straightforward, I think. So that's the end of the section 1. We're going to do one more section today. Okay, 4.2. Okay, we're going to talk about the exponential function in 4.2. So the exponential function is defined as f equal to b to the x. Okay, so we have a constant b which is positive and not equal to 1. Okay, and the variable is in the exponent, and x can be any real number. For example, the function f(x) equal to 3 to the x is an exponential function of base 3. Okay, b is called the base, by the way. Remember, make a distinction between the exponential function and the power function. And the power function is like x to the n, x squared, x cubed, So in that case, the base x is a variable, and the exponent is a constant. And in here, exponential function is just the opposite. The base is constant, and the exponent is the variable. Okay. make sure you know the difference. So for example, if I want to find f of 2, you just plug in 2 for x, we got 3 squared. Since f is 3 to the x, which is 3 squared is 9. Okay, so that's f of 2. F of negative 4, again plug in for negative 4 for x, so you get 3 to the negative 4, which is 1 over 3 to the 4 if you remember the properties of exponents. And the 3 to the 4th is 81 if you multiply 3 by itself 4 times. So that's 1 over 81, that's the f of negative 4. How about the f of pi? Okay, because x can be any real number. So what happens if x equal to pi? In other words, what's the function value when x equal to pi? So plug in pi for x, we got 3 to the pi from f, and we can approximate pi by 3.141597. And then if you do that using calculator, you can get about 31.54428. So that's the approximate value of f of pi. You can never get the precise value in this case because pi is an irrational number. But you can always approach its exact value by taking more and more digits for pi and taking the exponential, right? Well, graph is always important for any function. So for exponential functions, what's the graph? Well, very simple. For the exponential function b to the x, remember b is a constant, a positive constant, and not equal to 1. So we break it into two cases. For the base b greater than 1, the base b between 0 and 1. And turns out in those two cases the graphs are different. When the base b is greater than 1, then you get a graph increasing rapidly, but it passes through the 1 on y-axis. The y-intercept is always 1, no matter what the base b is. When it's greater than 1, you can take b equal to 2 or 3 or 5 or 1 or 100. It will always pass 1 in the y-axis. And on the left-hand side, it just approach the x-axis on the left and going up on the right without bound. So that's the case when the base be greater than 1. But if the base is greater than 0 and less than 1, between 0 and negative 1, 0.5, 0.7, 0.1, 0.2, whatever. And then you just get the decreasing curve, but it also passes through 1 on the y-axis. The y-intercept is always 1. In other words, for b to the x, no matter what the b is. And in the case b is between 0 and 1, the curve is decreasing and it approaches to the x-axis on the right side. And on the left, it goes up with bound. So in any case, the x-axis is always the horizontal asymptote for the exponential function, okay? b to the x. And on the other side, it just increases without bound. So this gives us the properties of the exponential functions f equal to b to the x from the previous graphs. First, the fx is 1 to 1. Okay, so if you draw any horizontal line, for both of those graphs, it only intersects with the curve at the most 1 point. Okay. It's 1 to 1 with the domain all real numbers and the range all positive numbers. So that can be read from the graph on the last slide again. The domain of this function, it essentially means what values of x corresponding to the curve Okay, you can see in both graphs the x values for the curve covers all the real numbers horizontally, right? And then the y values corresponding to the curve are all positive numbers. You can see both curves are on the upper half plane, covers the whole upper half plane. So the range of the function uh, is all positive numbers. Okay, so that's how you read domain range from a graph. Pretty straight, isn't it? The graph of f smooth and continuous with the y-intercept at 0, 1. So that's what we already discussed. We got a smooth curve when continuous, and the y-intercept is always 1 intercept. Part 3, if b is greater than 1, f is increasing, it goes up. That's the left graph. If b is greater than 0, less than 1, f is decreasing, right? So as x approaches negative infinity for b greater than 1, f approaches 0. As x approaches infinity, fx approaches infinity. So what does it mean by that? So for b greater than 1 on the left side, as x approaches negative infinity, so you look at the curve on the far left, then you're going to see it approaches the x-axis. That means fx approaches 0, right? And if you look at the curve on the left, on the right side, it goes up without bound. So as x approaches infinity, y approaches infinity, or fx approaches infinity. And when b is between 0 and 1, you look at the graph on the right. When x approaches negative infinity, so that's the piece in the second quadrant, it goes up with a bound. So fx approaches infinity. And when x approaches infinity, you look at the curve in the first quadrant, it approaches the x-axis, so y approaches 0, or fx approaches 0. So that's what it says in 3 and 4. So for if b is greater than 0, less than 1, f is decreasing. Okay, it's going down. That's the graph on the right, and in the previous page. As x approaches negative infinity, fx approaches infinity. As x approaches infinity, fx approaches 0. We just discussed it. Okay, let's just do a few simple examples of shifting of the curve. We discussed in the symmetry operations of functions. Let's just apply those symmetry operations to the exponential functions. So in this example, it asks us how to use the graph of f equal to 2 to the x to produce the graph of big F equal to 2 to the x minus 3 and g equals 2 to the x minus 3. Well, this is shifting. Okay, remember when you get the plus or minus to the original function. Specifically, big F is 2 to the x minus 3, so that's f of x minus 3. So you shifted the original graph of 2 to the x downward 3 units, okay? And for the g equal to 2 to the x minus 3, this time you shift horizontally because you get x minus 3 here to the right. So you shift the graph of f to the right 3 units to get the g, the graph of g. Okay, so you're going to see those graphs. The original graph f equal to 2 to the x and the big F 2 to the x minus 3 in the middle, and the g equals 2 to the x minus 3 on the right. Okay, we're just shifting down, shifting rightward, okay, so here are two other operations. How to use the graph of f equal to 2 to x to produce the graph of m equal to 2 times 2 to x and n equals 2 to the negative x. So these are two different, two other operations. When you multiply a number to the original function, you either stress or compress the original graph depending on whether the number you apply is greater than 1 or less than 1. Okay, you stretch it when the number you multiply is greater than 1. Okay, stretch vertically. If the number you multiply is less than 1, then you compress toward the x-axis for the original function. So in this case, we multiply by 2, so it's greater than 1, so you stretch. So we stretch the graph of f equal to 2 to the x vertically by a factor of 2 to get a graph of m. So that's what happens in the middle graph, right? Compress, stretch vertically. Well, in the case with 2 to the negative x, this time, as a different operation. You change x to negative x, so that's a reflection, if you remember what we did before about operations of graphs. You change x to negative x, so that means you're going to reflect the graph of f with respect to the y-axis. X changed to negative x, right? So the graph of n is a reflection of the graph of f equal to 2 to x across the y-axis. So you get the graph on the right side at the bottom, okay? From the original graph of 2 to the x. The last thing we want to say is the natural exponential function, or natural exponential functions. Well, as we said, the exponential function f equal to b to the x, where b is a constant. And the base b can be any positive number not equal to 1, right? Remember? If you choose this base to be a special number, we call it e, which is approximately equal to 2.718288183. That's perfectly fine. There's no problem for that, as long as it is a positive number, a constant greater than 0 and less than and not equal to 1. Okay. And this, if you use this number as the base for the exponential function, then we call this function f equal to e to the x as the natural exponential function. Okay. This number 2.718288183 approximately is denoted by e. It's an irrational number, and because this space is greater than 1, so it's increasing, as shown in the graph at the bottom. So how do you get this number e, the irrational number, a constant, just like a pi? The irrational number e is defined as the number that 1 plus 1 over n to the n approaches as n increases without bound. So what does mean by this? Okay, so you can calculate the value of 1 plus 1 over n to the nth power and see what you get. For example, if you choose n equal to 1, so you get 1 plus 1 over 1 to the 1. 1 over 1 is just a 1, so you get 1 plus 1 inside, which is 2. And the exponent is 1. So that's 2 to the 1, which is 2. Okay. But if you change n to 2, you get 1 plus 1 half to the square. 1 plus 1 half is 3 halves. You square it, and you get 9 over 4. So that's a little more than 2, right? 9 over 4. Well, you can increase n to 3. Then you get 1 plus 1 over 3 to the cube. 1 plus 1 over 3 is 4/3. You cube it, you get 64 over 27. Okay, that's then you increase that value a little bit more. So if every time when you increase the n by 1, you get this number a little bigger. The whole number 1 plus 1 n to the n as n increases. So this number increases as n increases. So you just keep increasing this and to a huge number. Then the number of 1 plus 1 into the n will approach this value e. It gets closer and closer to the value e 2.718281883. Okay, and that's how you define this e. It's called the limit of 1 plus 1 n to the n as n increases to infinity. All right. So that's how we define the irrational number e, how it comes from. Any questions for anything? So we finished 2 sections today, and I'm going to stop the recording now if you don't have any more questions.